Buenas tardes, vamos a continuar entonces con el seminario. Un gran gusto presentar que nos está visitando Michael Jablonski from Oklahoma. Nos va a estar visitando toda la semana que viene también, está en la oficina del CIEM, de visitantes del CIEM. Y bueno, el lunes va a dar el coloquio del CIEM. El lunes, no el 11, sino el 18. Y bueno, hoy va a hablar en el Seminario de Geometría sobre Einstein solvmanifolds as submanifolds of symmetric spaces.
Thanks very much. It's nice to be back in Córdoba. And thanks for letting me give my talk in English, because I'm just now starting to learn Spanish. The next time I come back, I will give my talk in Spanish. Okay, so here's the starting question. What are the homogeneous spaces? G mod K, which admit a G invariant Einstein metric. And just to remind everyone, by Einstein, we mean if its Ricci tensor is a multiple of the metric. So my interest, at least today, and almost always, is in non-compact spaces. So at least today, only non-compact. So let me give you some examples, some familiar examples. So the first one is hyperbolic space. Right, so this is the group of isometries, more or less, and this has constant sectional curvature, so of course it has constant Ricci curvature. You can upgrade this a little bit, and you could say G non-compact and semi-simple. With K a maximal compact. Oh, and there's a slight lie, I'll point it out. Then G mod K is symmetric and Einstein. So I guess if I want to be, well, with the usual metric, if I want to be a little more careful and a little more honest, then I would need to say simple, or else I might have to rescale my simple factors to get the constants in each simple factor to line up. And also there's a slight lie. If G is not linear, then you have some small issues with this group K. So maybe I'll just say linear. Okay, so if you notice, these actually share a property. So notice in both examples, there is a transitive solvable subgroup. And so both these manifolds are so-called solved manifolds. So that is both examples are solved manifolds. So here's a fact. To date, all known examples of non-compact Einstein homogeneous spaces have a transitive solvable group. So all known examples of non-compact homogeneous Einstein are solvable Lie groups. Well, I'll say are isometric too. Solvable Lie groups with left invariant metrics. And this is closely related to the so-called Alisevsky conjecture, but I won't say much about it. Maybe just to give some tangible examples, I'll write out what those solvable groups are for these two examples. So in the first case, so how can you see this as a solvable group? Well, it's just it's R acting on R in minus 1, and then here 1 is acting by the identity. So I guess I'm describing the Lie algebra. So I'll say this, at the Lie algebra level, so I have this Lie algebra, and I can take it simply connected Lie group, and that's going to act transitively on this space. And then in the other example, which is, what did I write down? Oh, I didn't write down another example. I'll give you one. Maybe like SU1n. So complex hyperbolic space. What would be a transitive solvable group? Well, again, it would be R acting on something, and here it would be the Heisenberg algebra of that dimension. And then how is this thing acting on there? Well, 1 is acting by the familiar 1-2 derivation. And what I mean is you have a nice derivation. So if I wrote out my Heisenberg as like x1, y1, x2, y2, and then I end with the center, you have a derivation that acts by twice the identity here, and then once the identity on all of this stuff. And that's the most familiar derivation, and it's the one that actually builds a nice Lie group to act transitively on this space. So it turns out that any Einstein solved manifold decomposes in a way that's similar to this. So a nice fact. (2008) I think. He can correct me since he's here. So around 2008, Laureate showed if S admits left invariant Einstein metric, then its Lie algebra decomposes nicely into the no-potent part, the no-radical, and then some other piece. And this other piece, where, well, I'll say a few things. N is the no-radical. A is abelian. Even more, A acts fully reducibly. This does not always happen. For example, you could always, right, have some no-potent thing acting on another no-potent, right? So in general, a solvable group doesn't have to decompose nicely into something that's abelian and acts well. And then finally, a couple other conditions that I should probably write down. A contains a very special element, a special pre-Einstein derivation. And then N has a Ricci-Soliton metric. And more or less, if all these things happen, then you get that the S upstairs also has an Einstein metric. And I say more or less because you need some eigenvalue conditions on how A acts. But otherwise, this is just about enough to guarantee that the bigger thing that you stitch together has an Einstein metric. So maybe some questions that I can write down. Yeah. So question. Is it common to admit an Einstein metric? Maybe another question worth thinking about, I think. Are there criteria which determine existence? And when I say criteria, I guess I mean some kind of algebraic criteria. I mean, these are some criteria, but if you go down this list, you'll see this one. And this one is that the no-potent part admits some kind of special geometry. So is there some kind of algebraic criterion that completely answers whether or not this existence happens? I don't know of any. And then maybe concrete examples. What are they? So let me say a little bit about that. So in low dimensions, everything is known. So fact, for n of dimension less than or equal to 6, n always admits a soliton metric. And so what this means is if you took a solvable Lie algebra and its no radical had a small dimension, and as long as you satisfied some of these algebraic conditions, then you're guaranteed that that solvable group has an Einstein metric. And this starts to break down in dimension 7. So it breaks down for so Edison, Fernandez, Colma classified those 7-dimensional those 7-dimensional nilpotents that emit a soliton. Right? Maybe some other familiar places to look, not just in low dimensions, but maybe at like 2-step nilpotent Lie groups. So fact. I don't remember when this was, sometime around 2008. Eberlein, my thesis advisor, and I showed 4, or maybe I'll say it like this, a generic 2-step nilpotent and admits a soliton. So if you're asking how common are these, if you can get your hands on some concrete examples, generically, if you picked a 2-step nilpotent Lie algebra, it should admit one of these metrics. But generic here means something like there's some kind of open dense set in the space of these. But if someone handed you one and said, does this one admit a soliton? That's actually a hard question. It's pretty hard to answer if a specific one admits it. So maybe I should note there are concrete examples of 2-step which don't admit solitons. So I guess in my thesis there were some, but there were also some nice examples for some other reasons in work by Ascari, I think in 2012, but around that time. So David Ascari built some nice examples that don't admit solitons. Okay. So let me come back to this question of concrete examples. So Hiroshi Tamaru built some new examples that are very concrete, and he did this in the following way. Let G be a non-compact semi-simple. And then take a parabolic subgroup P inside of G. So when I say parabolic, for example, you might think of something that's block diagonal inside of SLN. And then he says that this subgroup here, if I look at the orbit of this subgroup, that I'll build an Einstein submanifold using the submanifold geometry. So why does this work? It's kind of mysterious. If you look at the proof, it just happens. But it gives you a nice concrete set of examples. So maybe I'll write this out a little more precisely. So what do? You take P and you decompose into a Levy decomposition. So I have P equals the semi-simple part, and then I have its radical. And then if I take this solvable group and I look at the orbit, so this submanifold is Einstein. So there are a lot of questions that you might ask. One is, how many examples can be built this way? Well, exactly this way, a finite number, and that's because the parabolic subgroups are in correspondence to finite subsets of simple roots. So you can only get a finite number of examples this way. But you might be motivated to say, well, how many examples of Einstein solved manifolds can I get through this submanifold approach? That's a question. Or another question that I think is worth thinking about is this subgroup right here. So maybe I should point something out. So this radical part breaks up into its compact, and then a very nice, completely solvable part. So maybe I'll call this S, and I don't need to give that a name. And then if I took SLNR, let me write this down and then I'll start speaking again. So if you hand me any symmetric space G mod K, I can think of it as a submanifold of SLNR mod SON. And if I pause for a moment, I can think of this as a solvable Lie group, and that just the upper triangular matrices act on it. Well, I have this thing then, up to conjugation. That S is contained in there. So there are a lot of questions I can ask. One question would be, well, is it possible to say which subgroups of this one admit Einstein metrics? Or if I wanted, I could ask the same question for the generic G. I take the maximal solvable, so I take the Borel, and I throw away the compact part of the Borel, and I say, well, can I say something about these nice subgroups? When do they admit Einstein metrics? So the question that I'm going to focus on first will be this, and maybe if there's a little time at the end, then I'll get to that second question.
So any completely solvable group is a subgroup of GNI?
Yeah. Any. Yeah. Okay, so I want to think about this question, this submanifold question, and the way that I'm going to approach it is through this lens. So instead of just thinking about this orbit, right, this orbit actually is this subgroup inside of there, right, with the submanifold geometry, right? And that submanifold geometry is actually a left invariant metric on this group, right? Because if I have a left invariant metric here, well, right, it's still left invariant under S, right? So along S, I still have a left invariant metric. So here's the way I'm going to frame the question. So given a completely solvable Lie group S with left invariant metric, when does there exist a faithful representation B into the upper triangular matrices. Which is also an isometric embedding.
And on TNR, you are considering the Einstein method.
That's right. Yes. That was the next statement. Thank you. Yeah, I haven't told you the geometry here. So what's the correct choice of geometry? Well, I think it's the Einstein geometry because there's only one up to scaling. So here, TNR is given an Einstein metric. Which is unique up to scaling. So what's the Einstein metric? Well, it's easy to write down. If I take, so what is this? So let's do the following. Let's take X and Y matrices in TNR. Then we have the usual inner product that comes from, well, it's that. This is not the Einstein metric, right? So on the nilpotent part, this works, but you have to tweak it just a little bit. So here's what you do. On the strictly upper, you use B. On the diagonal, you use twice B. And then you make the diagonal and the strictly upper orthogonal. It looks a little bit funny, but it's the Einstein metric. It's the only Einstein metric on that Lie group, up to scaling, right? So while this might look funny, geometrically, I think it's the right thing to do. All right. So maybe I'll state a theorem. Just do it here. So let S be a completely solvable Lie group with Einstein metric. Then such a phi exists. So, I mean, I have a faithful representation, which is also an isometric embedding. By the way, I'll go ahead and be a little honest. There's, I could state this and say up to scale, because I never told you the scale of the Einstein metric. So if you fixed a particular Einstein metric, for example, this one, then this is only true if I say up to scaling. So up to scaling, this is true. So it's kind of like the Nash embedding theorem, except for the Nash embedding theorem, you don't have to say up to scale because, right, if you have a flat space, the scale is not really doing anything. Except here, this is not flat, so the scale, changing the scale does matter. Let me write down some consequences of this. So the first consequence, all Einstein solved manifolds arise as submanifolds of symmetric space, or of a symmetric space. Oh, and if you're curious, I guess, I guess it's worth saying, the choice of n here does depend on s, but there is a universal n that depends only on dimension. So depending on the dimension of this, there is a universal n that you can make work. Okay, so this answers, in a sense, part of the question I asked earlier, which was, Tamaru had these nice examples. They were very concrete, where your solved manifolds are submanifolds of symmetric space with the submanifold geometry, and it turns out that any Einstein solved manifold arises this way. But if you ask me, this is opaque, right? What he does is very concrete. You can see the algebra. Here it's more of an existence proof than it is concrete. Maybe I'll go ahead and say another corollary. Same results for Ricci solitons. And this is because of work of Jorge and Cynthia. You can always put a Ricci soliton inside of an Einstein space, and it has the submanifold geometry. So what do? Well, you put the Ricci soliton inside your Einstein, then your Einstein goes inside this other thing. So all the same results are true for Ricci solitons. A reasonable question. Can this be done for non-Einstein metrics? And the answer is, I don't know. All my friends said, the first thing you need is a non-example. Yeah, a non-example would make my theorem look much better, but I don't know of any. So it might be true that for any left invariant metric, this can always be done. But I don't know. The best I can say is for a small class that you can do it. And that small class is I guess I should put dates on these things. So on the archive in 2018. So. If n is a two-step nilpotent Lie group with any left invariant metric, such an, I don't know, I'll call it isomorphic isometric embedding exists. So for two-step nilpotent Lie groups, any left invariant metric works. Which, on the one hand makes you a little suspicious that this always happens, but on the other hand, these are so special that it's really hard to predict off of that. So maybe I'll give a sketch of the proof in the two-step case. It's and then I'll say how you tweak it and modify it to work in general. Okay, so the first thing, reduce to a Lie algebra problem. Right, so I guess, what do I mean? That is, we want I want this faithful representation which preserves an inner product. And then if it preserves an inner product, you can just see that lifts to a representation at the group level that preserves left invariant metrics. So that's the first step. All right. All right, so N is two-step. So I can do a couple things. The first thing I can do is I can write this like that, where this is the center, and this is just your orthogonal complement. Okay, and I also have the so-called 1-2 derivation. Right, what is this? This is, it's the identity on V and twice the identity on Z. So this is a feature of two-step nilpotent that other nilpotently groups don't have, which is one reason why maybe this only works in the two-step case, right? And maybe it doesn't work always. Okay, and what I'm going to do is I'm going to let S be that solvable Lie algebra, and if you notice, the center of S is trivial. Right? There is no center, because if there were a center, it would be inside of N, but this thing doesn't act trivially on anything in N. So this has no center. So the adjoint representation is faithful. And what I'm going to do is I'm going to take phi to be the adjoint representation of S and restrict it to N. So this gives me a faithful representation of N. And let's see what it does. So what does phi do? It sends me from N into GLN. Okay, and I can assume wow. It lives in some upper triangular, right? They're all conjugate, so it lives in some. Okay, I need to give this a metric so that this has a metric, and here's what I'm going to do. Using the inner product on N, we get an inner product B, right? This familiar trace on GL, right? So when I said using the inner product, that's where the transpose comes in. Okay, and now let's look at the image of things. So if I take Z inside the center, and I look at phi of Z, what do I get? Well, let's write this out. So So like this is RD, this is V, that's Z. Well, when this acts on the D.
Sorry, but phi is not faithful.
Yeah, it doesn't have kernel.
You restrict the faithful R to N, then, for instance, the center of N is acting.
Which, if I did add in here, you're exactly right. I would get a kernel. But because I'm doing add S, I avoid getting a kernel. You're right. Here, let me write it down here. I agree with you. On the nilpotent part, I agree. This thing is 0. But when it acts on the D, you get something non-zero, right? Because D of Z is 2Z. And so if I do this.
But phi is restricted to N, right?
It's add S restricted to N, but it's add S, not add N. I agree with you. If I had done add N, then I would get kernel, because you're right, I'm taking something out of the center. But, and that's, so on add N, 0. But on add S, when it hits D, right, what is this? Well, this is minus D of Z, so it's minus 2.
But D is not in N.
No, I agree.
So phi of Z is 0.
No. This is not add N, this is add S.
Yes, but D is not in N.
Am I saying something wrong?
Why you are applying phi of Z on D?
So this will be,
D is not in N.
this is wrong. I'm sorry, you're right. That was wrong. No, that's actually very important. You're right. Phi of N will give me things inside of GLS. You're right, thank you. No. Good eye. So what do you get? You get minus 2Z. So, I mean, this is pretty close, right? Because all you're really doing is doubling, right? That's all that's going on here. All right, so let's look at what happens with X and V. Wow. What do we get? 0 there, because X bracketed with anything in the center of N will vanish. X bracketed with the D will give me a minus X, and that's because D acts by the identity, and I just did the bracket backwards, right? So this is like X bracketed with a D. And then here, I get add X. Right, so this is a matrix, and if I apply it to elements in S, when I apply them to elements in V, it's just going to be X bracket that element, which is going to land me in Z. So I get this. So I'm close. I almost have a multiple of my original, except I've got some junk down here. So the question is there a way to strip off this junk? And the answer is yes. Here's a quick sketch of what you do. So instead of this phi, we're going to do, if there aren't objections, I'm just going to put a 1 on it. I'm going to try and make sure I hit them all. Okay. So the phi that I choose is going to be, I'm going to have phi 1, and then I'm going to correct it using another representation. And the part that I need to correct is not on z, I need to correct the part on v, right? Because I got what I wanted. It looks like my original inner product more or less, but then some of this junk. So the way you correct it is as follows. So let's consider this. As long as this C is large, so for large C, this whole thing is an inner product, right? And so what you can do is you can say, well, then there exists some L, and okay, so I only want to do this on V, so consider just on V, then there exists some L in GLV such that the above is equal to that, right? Because any two inner products are conjugate via another matrix, okay? And then how do you build this phi 2? Well, you could do something like this. You could make it conjugation by L precomposed with the same kind of representation we did before, except what do I mean by that? I mean phi on S mod Z. So what happens when I do phi on this? Well, I just get a multiple of the identity, and if I conjugate it, I know this is just a quick sketch, but let me say what you get. This simply rescales each factor, or it rescales the inner product on each factor V and Z. So this is the strategy, right? Is that I got it to rescale on one factor. On the other factor, I was close with a little bit of garbage. And so I throw on an extra representation piece to delete off the garbage. But now I've got the problem of rescaling by different factors on each one. So how do you correct that? You do it in a sneaky way. Here's what you do to fix the different rescalings. You precompose by an automorphism. And why does this work? Well, this works because A of t is e to the t on v, and it's e to the 2t on z, right? And so you can dial up your t, either dial it up or down, and then you get the same scaling factor on each piece. So this is how it works for the two-step case. How does it work in general? Well, in the general case, you have a pre-Einstein derivation, and you get more eigenspaces instead of just 1 and 2, and you try the same strategy. But instead of two factors v and z, you end up with several different eigenspaces, and then you kind of peel them off one at a time, throwing on these correction terms. So you get with your first eigenspace, you get exactly what you want, rescaling, then garbage, and you correct the garbage as you go down the line. So that's the strategy.
But then it seems to work for any grading.
Graded, yes. So as long as your derivation is symmetric, yes, you can do this. Well, yes, but the metric on n has to work well with the grading, right? So you need these eigenspaces to be orthogonal. So this works for a two-step n because the orthogonal complement of the center, you can always build a 1-2 derivation that's going to be symmetric, always. But in general, you don't have to have.
You would have only for the metrics as the gradient
Yeah.
is orthogonal.
Yes.
Here in two-step, these are all
Yeah.
orthogonal.
Yeah. And actually, the statement you're saying, so I'm not being entirely honest. The statement you're saying you actually need when you prove the result for Einstein spaces. To correct the garbage, you actually have to go beyond Einstein metrics. You have to use this bigger class of metrics where your grading's orthogonal. And, yeah. All right. How much time do I have? 10? So I told Jorge, in the US, the standard is 50 minutes. And I've trained myself to speak for exactly 50 minutes. So maybe I'll stop. I'll stop, but I'll say if you're curious about this other background question of when can certain special subgroups admit an Einstein metric. So for example, I'll just sketch this picture of the parabolic, where I had these nice block diagonal pieces, and then Hiroshi Tamaru says, this piece admits an Einstein metric. There are some results in this flavor that Carolyn Gordon and I have done, and I can tell you later if you're interested, but I'll stop here. Thank you.
So are there any questions or remarks? So you can always get like the same symmetric space. GNR.
Yeah, they all go into the same symmetric space, sure. But it sounds fancier if you say symmetric space.
Okay, so if I want my Einstein submanifold to be some manifold or some other symmetric space is
yeah, by the way, these, before I answer that, maybe I'll point something out. These aren't just embeddings, they're equivariant embeddings, right? So there's something stronger happening than just an embedding. And I'm not exactly sure about the answer, right? I know you can always take a symmetric space and equivariantly, maybe I'll ask an expert. If any symmetric space, G mod K, can go inside of one of these. But can this go inside of any of the other types as long as I picked a big enough dimension?
This is a Karolevich theorem, no? That there's any single. But this inside another one, you mean?
Yeah, like, can I put this inside of some, I don't know, SUPQ mod S.
for the hyperbolic space you will be in trouble.
Yeah, there's an issue of rank. Yeah, there's an issue of rank. Yeah. You're right. You answered yes, very good.
Yes. But okay.
Yeah, I agree because this is rank n minus 1, and so I couldn't fit it inside of a rank 1.
Any other question? Okay, thank you very much, Mike.